G'day, I'm James, and here's a curious little geometry puzzle. Just draw a polygon. I happen to draw a 5-sided polygon here, and do the following. At each corner, draw a little circle, just not a small one, but centered right at the corner. In fact, do it again at each and every corner, and do congruent circles. Circles all the same size, but not too big, so they actually just stay separate from each other. So I've got 5 circles, and some areas of these circles match the interior of the polygon. So let me just shade those yellows. So I've got a whole bunch of yellow areas from the corner circles. Do the same thing on the edges. Now draw some edges, some circles of the same size on each edge. So I want the centers to be somewhere on the edge. Congruent circles, yet again, every circle we're seeing is the same size. And they too have interior that sort of overlaps with the interior of the polygon. And I'll do blue area this time. In fact, you can see each of them has half their area is going to be blue. All right. And we'll do one more circle. We did corner circles, we did edge circles. We'll do one interior, one face circle if you like. And of course, all its area matches the interior of the polygon. All right, so we've got some yellow area, some blue area, and some red area. I claim the total yellow area, take away the total blue area, plus the total red area, 1 unit of area, equals 0. I claim we get that balanced formula there. Can you prove it? Can you prove it not just for a 5-sided shape, but any sided polygon? Cool. But actually, I put something up here. I said this is the 2-dimensional version of what I want to play with today. So I'll definitely go through this answer in this video. But let's actually go to other dimensions, because this is what blew my mind recently. Before I go up to 3 dimensions, it's kind of fun to think about what this result could be in 1 dimension. What would be the 1-dimensional version of this? So you wouldn't draw a 2-dimensional area of polygon. You'd draw, I guess, in 1 dimension, just that, a 1-dimensional line. And here, you wouldn't be drawing circles on the edges, corners, and inside. You have to be draw the 1-dimensional version of circle, which I guess is just like a little interval, like that. 1-dimensional circle. 1-dimensional circle. There's 1-dimensional circles on the corners, and here's how much of it matches the interior of the shape I first drew. I also need to draw a 1-dimensional circle on the edge, and here's how much of that interior matches the interior of what I first drew. And then I claim matching result here is the total yellow lengths minus the total blue lengths equals 0. In fact, you can kind of see that's true, because everything is congruent. This is kind of like a half interval length plus half an interval length. This is a full interval length. Half plus a half minus 1 does indeed equal 0. Beautiful. So there's the 1-dimensional version. All right, now, are we ready for 3 dimensions? Yes, the answer is yes. Here's the 3-dimension version. All right, so this time we have to draw a polyhedron and draw not intervals or circles. I'll now be drawing spheres everywhere. So forgive me, this is going to be a little bit tedious, but I'll do my best to draw some sort of picture that makes some sort of sense. Ooh, not a very good one already. I think I failed. Okay, I've got definitely some corners. Here are the corners. And I guess I also have some corners maybe at the back that we can't see, but okay, I'll do my best. All right, same idea. At every corner, every edge, every face, and every inside, we're going to draw spheres, congruent tiny spheres. So let's keep them small. So we'll draw at every corner a sphere. Every corner a sphere. So every corner we have, we draw a little sphere. Oh, I'm going to be a little bit tight there. My picture's not going to be very good. And each sphere intercepts the interior of the polyhedron. So I'll draw some yellow volume this time, where all these little corner spheres intercept the interior of the polyhedron. So a bunch of yellow volumes. A bit hard to draw. Hopefully you got the idea. So we've got a total set of volumes. I've got the total yellow volume is some value y. Now we'll do the same thing for the edges. Still congruent spheres centered on the edges this time. Centered on the edges. They're meant to be all the same size. My little spheres aren't very good. Oh, bad picture. That's very tight there. Okay, hopefully it's not too bad. It is certainly true. Each of these spheres intercepts the interior of the polyhedron. In fact, you can see this actually. This is on the edge. I've got one plane, one face here, planar face of the shape this way, and one planar shape of the face this way. So it's like the sphere is actually wedged between like 2 planes at an angle. In fact, people call that the dihedral angle between 2 planes, the angle the planes open up, the dihedral angle of the polyhedron for those 2 planes. So actually this sphere is like a wedge taken out, which I've been coloring blue as the next color. So blue wedge of volume there, a blue wedge of volume there, blue wedge of volume there, blue wedge of volume there, blue wedge of volume. Oh, this is very hard to draw here. And I can see I missed an edge. You also have a congruent sphere over yonder. with its blue volume in there and blue volume in there. Whoa, I think I did everything there. All right, so total yellow volumes, and I claim subtract the total blue volumes. But keep going, because now we've got faces. So let's draw a little congruent spheres at each face. So centered on each face, there's going to be a sphere there, there's going to be a sphere there, a sphere there, and a sphere for any back faces that we can't see. Now this time, okay, I've got a face and I've centered my sphere on the face, but actually you can see that half that sphere is going to have interior matching the interior of the polyhedron. Yellow, blue, red represents the next color. I guess it's going to be very hard for me to draw, but half this volume of this sphere is matching the inside. Half of this one is matching the inside. I'm not sure how to draw that. Half of this one's matching the inside, and so on. So I get a total set of red volumes. So yellow volumes minus blue volumes plus red volumes. And now I've got one more to do, which I'm not going to try to draw, but right in the center of the solid, like the interior of the whole solid, the three-dimensional solid, draw a sphere, and its entire volume will actually match the interior of the polyhedron. And let's pretend I colored it green. Oh, I don't have green, but plus green. I claim, if you match this alternative sum formula, even in 3 dimensions, that sum is sure to be 0. Wow. Wow. That blew my mind. Now, this is a result that's out there. I did look it up and it is around, but all the proofs I saw were like hard for my small brain to understand. So I actually want to sit down and see if we can actually prove that for ourselves. It's going to take a little bit of doing, so you probably might want to give a pause to this video. But let me clean the board first, and let's just at least do the 2-dimensional version right now before we go on and tackle the 3-dimensional version of the result, which I just thought was so neat and so cool. All right, I'm going to clean the board, back in a moment. Okay, so let's look at this 2-dimensional case. It's actually kind of charming. It's lovely. It just uses nothing but basic school geometry, and it's just charming in that way. So we've got all these circles, some drawn on the corners to give us some yellow areas, some drawn on the edges to give us blue areas, and one's drawn in the middle to give us a red area. Since all these circles are congruent, let's just assume we've scaled the picture so all the areas are 1. Okay, so circle area 1, circle 1, 1, 1, 1, 1. Great. I guess I've got a picture here of 5-sided shape, but we can have any number of sides. So I'm obviously going to do this for n equals 5 sides, but I bet everything we're about to do generalizes to any number n for the number of sides. Great. So we can get this. So let's assume we scale things to each circle as area 1. Then I know some of these areas. For example, red. The total red area is just that. It's going to be 1 unit of area, whatever that circle size is of 1 area. Great. Blues. Well, I've got n equals 5 sides, and each circle there has half an area. Oh, so the total blue area must be half plus half plus half plus half plus half. The total blue area is 5 halves. In general, it would be n halves. Great. Yellow. Yellow's the tricky one. What's the total yellow area? That's difficult because each piece here has a different fraction of that circle's area. Different fraction of the circle's area, but it actually depends on the angles we're talking about. So, let's give the angles some name. Let's call this angle alpha, angle beta, angle gamma, delta, and epsilon. Let's go very Greek right now. So, if this is area 1, and this is angle alpha, alpha is some angle out of a full turn, out of 360. So, this area must be the fraction alpha out of 360 of the area of 1. This area must be the fraction beta out of 360 of the area of 1. Gamma out of 360 of area 1, delta over 360 of area 1, epsilon over 360 area 1. So total yellow area is that fraction of 1 plus that fraction of 1 plus that fraction of 1 plus that fraction of blah, 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 blah. Common factor of 360, it's this fraction, delta plus epsilon out of 360 of 1. Great. So I need to know the sum of the angles of the polygon, interior angles of the polygon. Great, I can do that, because we know from school geometry that's always the number of sides minus 2 times 180, still out of a fraction of 360. So I know the interior angle formula. Great, I've got this, and 180 over 360, it doesn't matter, I'm using degrees, but I could use degrees, I could use radians, I could use anything I like here as a measure of angle, as long as I keep track of the fractions. All we care about is what fraction of turning I've got. This is just n minus 2 out of 2. And I bet n over 2 minus 1 minus n over 2 plus 1 doth 0 make. Beautiful. And there's nothing special about n equals 5 there. In fact, I did it without n equals 5. You just have more angles to play with. And it'll still be this formula. Grand. 2-dimensional case. Fabulous. So our challenge now is to try to make sense of, if I'm going to do this in 3 dimensions, those corner ones, I need some notion of angles at corners of a polyhedron and what fraction of, not area, but what fraction of volume they represent. So I'm going to be into some curious spherical geometry to even make sense of how to start adding up these fractions of a volumes in the 3-dimensional case. So we've got a bit of work ahead of us here. So maybe we want to stop there and say, that was grand, thanks James, and call it a day. That's totally fine. If you want to keep going, I'm going to keep going. There's more video to watch if you like. Okay, so let's go for the 3-dimensional version now. So remember, we have a polyhedron and we've got 4 different types of spheres. Corner spheres, edge spheres, face spheres, and that one inside sphere. Now the latter 2 are actually fine for me to think about because the very inside sphere, I know its full volume is actually part of the interior of the polyhedron. Each face sphere, so I've got some plane of the face, is centered on the face, so I know that half the volume of that sphere is inside the polyhedron, the other half isn't. So I know the fraction of volume inside is 1/2. It's actually just the edge spheres and the corner spheres that make me nervous. So I got some fraction of the volume of the sphere inside and some even weirder fraction of the volume of the sphere inside. That can be hard for me to think about. Of the 2, I think the edge sphere is the easier one to think about, and I'm going to think about that one first, because what's really going on here? I can see there's kind of like 2 planes coming together on a line, so I can be the line, and here's 2 planes, so that's the 2 faces of the shape meeting along a line, and I've got some sphere centered right on that line. So let me draw that. Let me see if I can draw that. So I've got some line where 2 planes that match the faces of the sphere come together. You see I've got like 2 book leaves, how am I doing? It's trying to come together here like this. And some sphere centered right on that edge. Now, they could be, who knows what angle this is, some sort of strange angle. Let me call that angle alpha for now. So these are coming at some angle alpha to each other. People call this the dihedral angle of 2 faces, the dihedral angle. So if 2 faces come at a certain angle, people call it the dihedral angle for the polyhedron for those 2 faces. So I guess every pair of faces have their own dihedral angles. And that's good, because if I know the dihedral angle, I know that represents some fraction out of 360 degrees, some fraction of full turning. If you think about it, I've kind of got that going on for the volume of the sphere. I can see that the sphere is actually being, just that little wedge is actually being sliced out and matching the interior of the polyhedron. So the fraction of volume of the sphere inside this polyhedron matches alpha out of 360. Okay, did you catch that? Alpha gives me an indication of what fraction of the sphere's volume is inside the polyhedron. So if I've got dihedral angle here, dihedral angle alpha, then I know the volume inside is that fraction, alpha out of 360 degrees. I'm using degrees, I'm using radians, alpha out of 2 pi. We actually have to choose some units soon. Some fraction out of the full turn of the volume of the little sphere, volume of the sphere. So I know that fraction of the volume of the sphere would be inside the polyhedron. So to understand what's going on in the edge spheres, I need to know all about the dihedral angles. Okay, nervous, but I could probably do something there. Those ones make me really nervous. All right, so what's going on with those corner ones? So what about those corner spheres? What do I need to know to make some sense of those? Let me see if I can draw the picture, make it a little bit bigger here. So I have a feeling, in fact, we've got lots of faces. I've got this front face coming through the center of the sphere, this side face coming through the center of the sphere, I've got this back face, or what else is going on, maybe more things going on in the back coming at the center of the sphere. I've got all these planes coming up to the center of the sphere. All right, so it's kind of like what's happening there. All these, there was just 2 planes coming to the center of the sphere, but now I've got lots of planes coming to the center of the sphere. Ooh, lots of planes coming to the center of the sphere. That makes me think of something. Because actually, go back a notch. You might learn, if you ever do a little bit of spherical geometry, that people love planes that go through the center of the sphere. Because if you've got a plane that slices through the center of the sphere, it actually slices the sphere into a great big circle. In fact, it's the biggest circle you possibly get, and it's called a great circle. So I've actually got lots of little great circles going on from each of these planes. So I can see that this edge here intercepts at that point, this edge is at that point, it's at that point on the surface of the sphere, and it makes off this little great section of a great circle right there on the surface of the sphere. I get another section of a great circle on the surface of the sphere from that plane, between those 2 points. And let's just assume there's one plane at the back. I'll get another great big section of a great circle at the back, from that back plane. So actually, these three planes in this picture give me on the surface sections of a great circle, and people call those spherical polygons. And people know lots about the areas of spherical polygons. So I'm going to talk about the areas of spherical polygons too, because if you know the area, at least you know what fraction of area you've got. I bet that's the same as the fraction of volume we're talking about. Because look at this. Because everything's going to the center. If I know, say, that area there on the surface represents 1/8 of the whole surface area, then I know this wedge will represent 1/8 of the whole volume. If this surface area represents, 1/7.222 of the whole volume, whole surface area, then that volume will represent, that wedge will represent 1/7.222 of the whole volume. So actually knowing the fraction of surface area by the spherical polygon actually tells you the fraction of volume I've got. And I want the fraction of volume, therefore we can focus on the fraction of surface area, and I know something about surface areas of polygons on spheres. So that means in order to really understand this question, I need to understand this surface areas of polygons. Except I've got a bit more information. I can see dihedral angles happening everywhere, because I not only know they've got sections of great circles here, I know the angles between these sections. For example, this section here and this section here is coming from this plane and that back plane. That's what we're calling dihedral angle alpha. That'll be the dihedral angle alpha. And this one here is actually another dihedral angle between, where am I? This plane and this plane. Wherever they meet, I'll call that angle beta. That means these two sections of great circles are meeting an angle beta, and these meet as another dihedral angle, call it gamma. So actually, understanding the fraction of volume here is all about the dihedral angles as well. Everything seems to be about those dihedral angles. All right, I've got a path, not quite sure where it's going, but now I want to know what's the area of a polygon drawn on the surface of the sphere in terms of its angles. If I've got that, then I've got this in terms of angles, this in terms of angles, and hopefully something magical will happen after that. All right, so sidetrack. How do I work out the surface area of a polygon drawn on a sphere? Okay, we'll do that next, and then come back to this. Back in a moment. I'm going to clean the board. Okay, so let's now talk about surface areas of spheres. First of all, I know the general form of the surface area of a sphere is 4 pi r squared, where r is the radius of the sphere. All right, so the surface area of the whole thing, done. So let's now start drawing some great circles and make spherical polygons. Now I'm going to draw one great circle first. Here he comes. I'll go from North Pole to South Pole, and I'll go back up again. Great. And then I will draw a second one, and I'll actually make a two-sided polygon, but I'll go from pole to pole. In fact, I'll get rid of the back because it's going to be confusing in a moment. But it too will wrap around all the way down and back up again on the other side. And let's assume I've done this at some angle alpha. Some angle alpha. All right, some angle alpha. Now, I'm going to ask, what's the surface area of that two-sided polygon, that bigon drawn on the sphere? So you actually have two-sided polygons on spheres. There's one. Now, I'm seeing pi in this formula, which makes me think, rather than get a mixtures of pi's and 360s everywhere, I'm going to cross my fingers and hope lots of pi's cancel out if I go with radians. So if you remember, radians says take one full turn, 360 degrees, so one full turn, and match that with the distance around a basic circle. The distance around a basic circle will be radius 1, the distance around will be 2 pi radians. So I'm going to think about one full turn in my mind is no longer the number 360, one full turn is now 2 pi. All right, because that might get rid of some pi's. I'm just doing wishful thinking right now. Don't know if it's actually going to work out. We'll find out. So, all right. So if this is some angle alpha, this is some fraction of a full turn, some fraction of 2 pi. Oh, so this must be that fraction of the whole surface area. So the area of this bigon, this two-sided polygon, must be that fraction out of 2 pi of 4 pi r squared. Oh, cancel out the pi's, I love it. 2's and 4's cancel, so what is it? Alpha 2r squared. All right, so the area of a bigon is alpha 2r squared if its angle is alpha. Great. So now I know the area of at least a two-sided polygon on a sphere. Let's now go for a three-sided polygon, a spherical triangle. Here's the lovely thing about spherical triangles, because I think I can think of it as follows. Let me not draw that one. Let's not draw an equator. We know that circle represents a three-dimensional shape. It's going to have some section of a great circle. So I'll draw a great circle like that, and I want some section of it. I want that part. Then I want another section of a great circle. and maybe I want this part. So there's two sides of my spherical triangle, and I want another section of a great circle, and it keeps going around as well, and I want this part. I want the area of that, I'll call that area X. I'm going to make my picture really messy and try to now draw the back parts. So this great circle does actually wrap all the way around. This one actually does wrap all the way around. Oh, this is going to be pretty bad. And this one actually wraps all the way around as well. All right, but here's the thing. I've got my front triangle, and you can kind of see by symmetry, since everything goes back and redoes itself close up on the other end, I've got an exact copy of that same triangle on the back of the sphere. Do you see it there in the dashed lines? In fact, I've got, what have I got? What have I got? I've got actually the sphere divided in lots of regions. I've got one region X at the front, I've got a copy of that region X at the back, and I've actually got all these bigons everywhere. I've got lots of bigons. In fact, if I call this angle alpha, the dihedral angle there, the two planes that go through there, I can see I've got this bigon that wraps here and comes back here. That's a bigon of angle alpha. I know its area. If this is angle beta, I've got beta and its bigon that comes all the way back here, which is given by that formula, beta 2r squared. If this is angle gamma, I've got another bigon which wraps this way, whose angle is gamma 2r squared. So I know lots of areas in this picture, and I want the area X, and I bet I can work it out. So, can we remember that? Alpha 2r squareds for bigons? Let's go for it. Let's go for it, because I'm running out of room. So what have I got here? Let me call X and the rest of this A. X and A. So X plus A, that area in total is the area of a bigon. That is with angle alpha. So it's alpha 2r squared. Let me call this part down here B. So X plus B makes another bigon. X plus B is beta 2r squared. And let me call this one opposite gamma the C. So that part there, X plus C, makes another bigon. So that's be gamma 2r squared. And let me add these together. X plus X plus X plus A plus B plus C. So two X's plus an X plus an A plus a B plus a C, and obviously I'm being sneaky here, is alpha plus beta plus gamma 2r squareds. All right, so far so good. Why did I not just write 3x? I went X plus A plus B plus C. Well, look at the symmetry. X plus A plus B plus C is what I'm seeing on the front, and what you see on the back is another X, and you actually see another A, because it's actually going to be the one that's opposite. It's alpha. Its alpha's over here. This is the other A. This is the other B. This is the other C. So actually this is half the whole sphere. 2 x's is half the whole surface area, pi r squared plus alpha plus, equals alpha plus beta gamma, 2r squareds. Whoa. So actually, I've got a formula for x now. Solve for it. X must be, what's this? 2r squareds. My board technique is lousy. Lots of 2's everywhere. 1x, 1 pi r squared, alpha plus beta gamma r squared. I see that x is actually alpha plus beta plus gamma minus pi times r squared. The area of a spherical triangle is sum up all three angles in radians, take away half a turn, pi, and whatever that number is, whatever that axis is, times by the radius squared. That's it. The area of a spherical triangle is, normally the area of a triangle in planar geometry is just 180 degrees, pi. What they're saying here, no, actually in spherical geometry, things are weird. You'll get angles out to more than 100 degrees, more than pi. Take the excess, add up the angles, and say how far over pi are you, and multiply that by r squared. That's its area. Wow, that's amazing. And then I'm going to just let you check this for yourself. That was triangles, but the thing is, any spherical polygon is just a bunch of triangles. So let's see. So if I draw a sphere, not very sphere-like, but I won't bother drawing the equator here. But if I gave you, say, a 5-sided shape, okay, all little sections of great circles, you could chop that up into triangles and apply this formula 3 times. 3 times. You'll get this angle alpha, this angle beta chopped into 3 parts, angles gamma, angle delta chopped into 2 parts, angle epsilon chopped into 2 parts. But I bet in the end, you could prove that the area of that polygon is the sum of all the interior angles minus what the sum should be. Normally the sum is n minus 2 times pi, then r squared. There is the general formula for the area of a spherical polygon. So we now are set to start playing with that three-dimensional version of that results about fractions of volumes of spheres. Okay, I'm ready for it. I'm just going to keep going. I'm on a roll. Back in a moment though. Okay, now we're ready to bring everything together. So we've got this polyhedron, we've got all these corner spheres, we've got these edge spheres, we've got this face spheres, and that one interior sphere. And apparently this weird alternating sum of their volumes is going to give us 0 on the nose. Okay, let's do it. Let's make it happen. Let's see why that's true. Just to make our lives easier, so let's assume each sphere is scaled in such a way that their radius is going to be called 1 unit. In which case their surface area is going to be 4 pi 1 squared, 4 pi, and the volume is going to be 4/3 pi 1 cubed, 4/3 pi. Great. Also, to bring us aligned with a standard language and notation in polyhedron theory, people tend not to call these corners, they tend to call them vertices. And we'll let V be the number of vertices we have. So that means we have V vertex spheres. E is the number of edges we have. So we have E edge spheres. F is the number of faces we have. F face spheres. And that one interior sphere. All right, so far so good. And now we want to add up the volumes that each sphere has of each type that matches the interior of that of the volume of the polyhedron, the interior region of the polyhedron. All right, okay, here goes. I'm going to do the easy ones first, faces. I didn't draw one here, but remember each face sphere just sits on a face, center on the face, so we know that half the volume, half of 4/3 pi, 2 pi over 3 matches the interior of the polyhedron, the other half doesn't. So that means I know how to work out the sum of all the volumes from the face spheres that match the interior of the polyhedron is given as follows. I'll call it the sum of F volumes, which I guess sounds a little bit weird, but I think we know what it means. It will be one face sphere has half of 4 pi over 3 for its volume. Do it for each face there is. I'll be doing that F times F. So let's say 2 pi over 3F is a formula for the volume coming from the face spheres that matches the interior of the polyhedron. Great, 1 down, 2 to go. All right, the next easiest one for my brain is the sum of the E volumes. The sum of all the volumes that come from the edge spheres that match the interior of the polyhedron. Okay, so let's look at one edge sphere first. So remember, it comes from two planes coming together at some dihedral angle alpha. So let's say dihedral, angle alpha. Okay, bad handwriting. Okay, so be it. All right, so we know actually alpha gives us that is a fraction of a full amount of turning, and that fraction of full turning is the fraction of the volume of the sphere that's in the interior of the polyhedron. So we want the fraction of turning given by alpha, so that's alpha out of 1 full turn. Remember, we're doing radians to make our pi's disappear and make our lives easier. That fraction of the volume of the full sphere, that fraction of 4 pi over 3, is the volume that's inside the interior of the polyhedron. Great. That actually simplifies a bit. 4 pi over 2 pi is 2. So the volume that's inside the sphere is 2 pi over 3 for a dihedral angle of alpha. Now, we're going to add these all up. For this edge, this edge, this edge, this edge, this edge, we have lots of different dihedral angles. So this could be dihedral angle number 1, so number 1, plus this formula for dihedral angle number 2, alpha 2, for alpha 3, for alpha 4, and so on. And I want to add them all up. So the notation I'm going to use here is the standard sigma notation for summation, summing over all possible dihedral angles, all alpha i's, alpha 1, alpha 2, alpha 3, and so on. So there is a formula for the volume coming from all the edge spheres that sits inside that polyhedron. All right, actually there's a common factor of 2/3, all the sum, so actually I could actually make this a little bit simpler. This is 2/3 times the sum of all the dihedral angles. Okay, maybe that's a little bit better. Okay, grand. All right, 2 down, 1 more to go, the scary one. All right, let's do the sum of all the V volumes, all the volumes that come from the corner spheres that sit inside that polyhedron. Let's do one at a time. One corner sphere. Now remember, we realize that the surface area of the polygon, the spherical polygon it gives it, is actually the key thing to understand what's going on. So here goes. So this corner sphere actually gives us a little surface area polygon, a spherical polygon. We know its area to its volume actually matches the fraction of the volume that's inside the polyhedron. So we need to know the area of this thing. Now, it's going to be composed of some faces. This actually looks like it's got 3 faces, but maybe it's like, n faces. We'll do it n faces. And we know we have lots of different dihedral angles here. There's dihedral angle alpha 1, dihedral angle alpha 2, dihedral angle alpha 3, and so on and so on and so on. So let's say we have n faces, even though this picture has 3, if you can see it, with dihedral angles alpha 1, alpha 2, alpha 3, up to alpha n. So we know the area of the spherical polygon is going to be the sum of all the dihedral angles, which in planar geometry should normally be n minus 2 times pi. But the area turns out to be that difference times radius squared, 1 squared. All right, so there's the surface area of that little spherical polygon. And we know what fraction of the surface area is that? Well, that fraction is that area divided by the full surface area. So that's the fraction of surface area that takes. And we know that fraction of surface that takes matches the fraction of volume we've got. We've got that fraction of the full volume. So we've got this fraction of the full volume, and the full volume is what? 4 pi over 3. So, oh, that's it. So this corner sphere is actually giving us this volume. Okay, this looks nasty, but let's just keep with it. 4 pi's cancel, which is great. There's a 1/3 in front of everything. So I could rewrite this as, all right, messy board technique. But this is 1/3, 4 pi's cancelled, the sum of all the dihedral angles minus this, minus n pi plus 2 pi. Let me expand that out. Minus n pi plus 2 pi. All right, so there's a formula for that volume. We've got that volume there. And we're going to add this up over all possible corner vertices, all corner spheres, all vertex spheres. Now we're going to be careful here. Because I'm going to do that for this one. I'm going to do it for this one. But look at this. We'll be summing this angle alpha 1, this guy. It gets used for this corner sphere, and it gets used for this corner sphere. It actually gets used twice when we do the whole sum. This one will get used twice for that corner sphere, that corner sphere. This dihedral angle will be used twice, that corner sphere, that corner sphere. So when I sum up all these dihedral angles, I'm actually adding up all the corner dihedral angles, each dihedral angles, twice. So when I do the sum of all this over all the corner spheres, what I'm really going to get is the sum of all the dihedral angles twice with a factor of 1/3. So twice 1/3 of everything is going to be 2/3 of the sum of all the dihedral angles for that part. I'm also going to be summing, watch out, n pi for every corner sphere. N pi, what's n? N was the number of edges I assumed I was working with. How many edges do I have for that spherical polygon? Well, I get 1 edge for each face I'm working with that comes up to that center of that sphere. Number of faces. But the number of faces actually equals the number of edges. The number of edges that comes up to that corner of that sphere actually equals the number of faces coming up to the corner of the sphere. So actually, this n equals the number of edges that come up to this center of that sphere. Brilliant! Number of edges. Warning though, this edge gets used twice. It gets used for this corner sphere and it gets used for this corner sphere. This edge gets used twice for this corner sphere and this corner sphere. This edge gets used twice, that one and that one. So actually, when I add up all the edges that come to this corner, and add up all the edges coming from this corner, add up all the edges coming from this corner, I'm actually going to add up all the edges twice. So when I add up all the n's, I'll actually get all the edges twice with a factor of pi. So I do the sum over all the n pi's, I'll get twice the number of edges with a factor of pi. Whoa! And finally, and it's a factor of 1/3. Watch out, there's a 1/3 in front of everything, so 1/3 of that. Whoa! Okay, and finally I'm going to sum up all the 2 pi's. So I go 2 pi for this vertex, a 2 pi for this vertex, a 2 pi for this vertex, a 2 pi for this vertex. I'll be doing that v times 2 pi's. So plus I'll get 2 pi v times with a factor of 1/3 in front of everything. There is a formula for the volume coming from all the vertex spheres added together. Whoa, okay, but I can see right now, we are kind of there. This is lovely, this is fabulous. All right, so what's going on? So the claim was, if I take all the vertex volumes, this formula, 2/3 sum of all the dihedral angles, minus what, 2 pi on 3e, plus 2 pi on 3v. Subtract all the edge volumes, minus 2/3 the sum of all the dihedral angles, and add all the face volumes plus 2 pi over 3f minus the volume of that one interior one minus 4 pi on 3. There it is, the full volume. What do we get? What do we get? Okay, we get a mess on the board. But I make some space. Here goes, make some space. What do I get? This equals, well, look at that. All the dihedral angles don't matter in the end. Don't matter when I do the sum. So I get, what am I getting? I'm getting 2 pi over 3 is a common factor of everything. So I get a v minus an e plus an f minus double 2 pi over 3. And there's a very famous formula, Euler's formula, that says that v minus e plus f minus 2 will be 0. 2 pi over 3 times 0, indeed, it is 0. Actually, this idea of looking at volumes of spheres placed on vertices, edges, faces, the middle, and that their sum is 0 is really just Euler's famous formula in disguise in the end. What I love about it, you can actually see that result in 1 dimension, 2 dimensions, and now 3 dimensions. And you know what? If you actually make sense of volumes of hyperspheres in higher dimensions, in which case the result is actually true too in higher dimensions. It keeps on going. So this is really, in the end, another interpretation of Euler's famous formula for the vertices, edges, and faces of a polyhedron. Whoa, whoa. So I invite you to go through the analysis, if you like, for the 4-dimensional case, and have loads of fun thinking about what that means. How do you interpret fractions of volumes of 4-dimensional spheres? Whoa, mind-blowing and fabulous.